So welcome back to week 3, lecture 1 of statistical methods. This week we will be covering the topic of z-scores and probability and the standard normal distribution. Now, just something to keep on your radar is that quiz 1 begins next Monday, September 14th, and it will cover material from weeks 1 through 3. It will go live on the course page on September 14th, and it will be due Friday, September 18th at 11:59 p.m. Now, keep in mind that there will be no time limit once it is started, as long as it is completed before the due date. It will be multiple choice format, and feel free to use all of your notes and materials that are available, and review the Kahoot question sets to get a sense of what will be asked on the quiz. These will most closely match the type of questions you will see. Many of them might even appear on the quiz. So last week we talked about sum of squares and variance, and to get a better visualization of how this works, you can look at this link here, which will open a Shiny app that will display to you how sum of squares and variance is calculated and how different distributions with different levels of dispersion look in terms of sum of squares and variance on an actual histogram. So by now you should know how to visually depict a distribution of scores using frequency tables and histograms. You should know how to calculate and interpret the mean and the standard deviation of a variable measured in a sample of individuals. And these topics are the heart of descriptive statistics, allowing us to quickly communicate to others the shape, central tendency, and variability of a distribution. Now, the goal of week 3 is to begin easing you into several concepts that will become crucial later on in this course. Specifically, the ability to quantify the extremity, or the measure of how extreme a statistic is within a distribution made up of that statistic. So, for example, a distribution comprised of entirely sample means from a particular population, or even a distribution of raw scores from a particular sample. Now, knowing things about how the distribution of a statistic looks is the other topic, so that we can make probabilistic statements about scoring at various places along the x-axis. So, for example, what is the probability of finding a z-score between 0 and 1, or a z-score between -1 and -2? So here we'll be using the normal distribution and the standard normal distribution. Now, these concepts are important because they lay the foundation for inferential statistics. So that is going beyond our data to generalize a research finding to a population of individuals. So we'll begin by learning how to numerically express the extremity of a single person's score within a distribution using z-scores. Now, most of the time, researchers aren't really interested in statistics based on individual scores, but this is intended as a teaching tool to put some key concepts in place. Later, we're going to apply the same logic we learned here to statistics like the sample mean, as opposed to individual scores. Now, when we talk about z-scores, we're going to talk about extremity. Now, by extreme, we mean that a score looks very different than most other scores in the distribution. So more specifically, if a score is much higher or much lower than a typical score in a distribution, for example, the sample mean, it will be considered extreme. So a height of 4'6" or 6'8", these are both extreme scores in the distribution of height. So are IQs of 65 or 135, or a yearly salary of $5,000 or $500,000. So another way of thinking of this is that these above scores would be fairly unlikely or improbable to occur based on what we know about the distribution of these variables, because they are so extreme. Now, a z-score tells us how many standard deviations away from the mean is a particular score. So if an individual has a z-score of +3, it means that their score is 3 standard deviations above the mean. Now, on the other hand, if somebody has a z-score of -3, that means the score is 3 standard deviations below the mean. So is this extreme or not? Well, this means that the score is 3 times the average deviation from the mean, or the standard deviation, so it's fairly extreme. Thus, the greater in absolute value the number of a z-score is, the more extreme it is as well. So for example, Jerome completes a 7-point satisfaction with life scale and scores of 5. Should this be considered an extreme score? The question really is, extreme in relation to what? To answer this, we need to know some information about how other people score on the scale, so what a typical score looks like. So let's say we administer this measure to 100 people and now have a distribution of scores with the following characteristics. A mean of 3.4 on the 7-point scale with a standard deviation of 1.47. Now we can see that Jerome is above average and that his score varies from the mean by more than 1 standard deviation, so more than the average deviation. Now Jerome's deviation score is 1.6. Again, that's the score minus the mean. So here is the average score. Now here is Jerome's score. Now a z-score neatly expresses the extremity with a single number. It uses the mean and standard deviation to answer how many standard deviations above or below the mean is this particular score. So in our example, Jerome's score is 5, and this was 1.6 units above the mean, so a bit more than 1 standard deviation of 1.47 in this sample. So imagine that another person on this distribution scored a 2, and this is 1.4 units below the mean rather, and that's a little bit less than 1 standard deviation below the mean. So Jerome's z-score is 1.09, since his score is a little bit more than 1 standard deviation above the mean, whereas this other person's z-score is negative 0.95, because this person's score is slightly below 1 standard deviation below the mean. Thus, z-scores give us an idea of how extreme a score is in comparison to the typical score in a sample, that typical score being the mean, in units of standard deviation. So the greater the z-score in absolute value, the more distant, either in the positive or negative direction, that person's score is from the mean. So here's one application. So a researcher administers a measure of creativity to a sample of participants. Now, if an individual participant's creativity score equates to a z-score of -2, what does this tell us? How about a person with a z-score of 0? Now, how about somebody with a z-score of +3? So the first one, if somebody's creativity score is a z-score of -2, what does this tell us? Well, this tells us that this person's creativity score is 2 standard deviations below the mean. Now, a person with a z-score of 0 means that they scored directly at the mean of this creativity scale. Now, a z-score of +3 means that this person's creativity is 3 standard deviations above the mean. Now, both -2 and +3 are somewhat extreme values. Whereas a z-score of 0 is not an extreme value at all. In fact, it is the expected value of this distribution because it scores directly at the mean. So to calculate someone's z-score based on their raw score, so that's their original ordinary score on the variable, or x, we use, simply take an individual's deviation score, so the distance from the sample mean, in other words, the score minus the sample mean, and divided by the sample standard deviation. Now, in some situations, you might also want to work backwards using somebody's z-score to calculate their raw score. To do this, you multiply the z-score by the standard deviation and then add the mean. So for example, what yearly income would be equivalent to a z-score of 1.5? Now I'd like you to quickly solve these three problems. The psychologist asked participants to research and come to an opinion on a political issue about which they previously knew very little. And the dependent variable here, or what the researcher was measuring, is how much time in minutes participants spend researching before arriving at an opinion. Now, the mean for this sample was 14.2 minutes, while the standard deviation was 4.7 minutes. Now, I want you to calculate z-scores for individuals who researched articles for 15.5 minutes, 4.9 minutes, and 50 minutes. Now, you can pause the video here and try to solve these. So for this first problem, our score is 15.5. So if we subtract the mean of 14.2 from that and divide by the standard deviation, 4.7, we get 0.28. So that is our z-score, a z-score of 0.28. So 0.28 standard deviations above the mean. Now the second one, we have a score of 4.9. Dividing that, or rather subtracting the mean from 4.9 and then dividing by 4.7 yields negative 1.98. In other words, this person scored almost 2 standard deviations below the mean. Now, the final score is 50 minutes, so subtracting the mean from that and then dividing by 4.7 yields 7.62. Now, this participant scored an astounding 7.62 standard deviations above the mean. So this final score here is incredibly extreme. This is most certainly an outlier. So dividing by standard deviation is a way to standardize this score to whatever the scale being used is. So for example, if a deviation score x minus m of, for example, is a standard deviation score x minus m of 10, big or small, and this totally depends. So if this was on a 10-point scale, it's a huge deviation score. But if this scale is a 1,000-point scale, it's very tiny. So dividing by the standard deviation frees a z-score from whatever the actual scale units are and allows for comparison across different measurement formats using standardized scores. So an example of an application is if two researchers are measuring the same variable but using different scales. We can then use z-scores to compare scores across these different scales. Now this gets around the issues present when comparing raw scores, which won't make any sense at all if different scales are used. So let's say one researcher measures life satisfaction on a 7-point scale and finds a mean of 4.3 with a standard deviation of 1.2. And one person scores a 3 on this scale. Now another researcher measures life satisfaction, so the same construct or the same variable, but uses a 50-point scale and finds a mean of 27.0 and a standard deviation of 1.49, or rather 14.9. Now let's say one person scores a 40 on this scale. Now comparing 3 and 40 are not very meaningful because different methods are used in regard to measurement. But if we calculate the z-scores, so 3.3 minus 4.3 divided by 1.2, yielding us a z-score of negative 1.08, and 40 minus 27 divided by 14.9, yielding a z-score of 0.87, these two numbers are now in the same units, and thus can meaningfully be compared. So z-scores allow us to compare scores that are measuring the same thing on different scales. So if you would like, please watch this YouTube video pertaining to z-scores for some more information. And then I have another in-class problem for you to work through. So a researcher asks a sample of n equals 200 subjects of incoming freshmen to estimate what their GPA will be at the end of their first year in college. Now the mean obtained here was 3.4 and the standard deviation was 0.4. Now, Jason predicted a GPA of 2.5 for himself. What is Jason's z-score? Then I would like you to interpret Jason's z-score and explain it verbally, and then determine what raw score is equivalent to a z-score of +1 for this distribution. So I'd like you to go back through the slides and find the formula to solve these problems. Now for Wednesday, I'd like you to finish the reading assigned in the weekly calendar and begin prepping for quiz 1, which will be on Monday, September 14th, and it will cover material from weeks 1 through 3. Now again, this will go live on Monday the 14th, but will be due Friday the 18th at 11:59 p.m. And once you start the quiz, there will be no time limit for how long you can take to complete it. You can also use materials such as slides to work through the quiz. And in addition, you can also use the Kahoots to study. These Kahoot question sets will be a very good tool for studying for quizzes because the types of questions you'll see there will be on the quiz. Now, some of the same questions might appear. I will change the numbers if it's a computation problem, so keep that in mind. Thank you.